Hello everyone, welcome to this session. Today's where we are discussing about the sound waves. In this session, we'll discuss about the resonance. So that's what we'll cover in this video. Let's dive into it. We'll start with the introduction to this, the concept of resonance as applied to the sound waves. The resonance, this is just a phenomenon that occurs when a given system is driven by another vibrating system or the external force to oscillate with greater amplitude at these specific preferential frequency. So that's how you can simply define a resonance as just that kind of a phenomenon that it occurs to just a certain system that is driven or brought by another vibrating system, or just that kind of external force that is there just to oscillate with the great amplitude to a specific preferential frequency. Now, frequencies at which the response amplitude is a relative maximum, just known as the system's resonant frequencies or resonance frequencies. So there are these frequencies at which the response amplitude is a relative maximum, and they are known as the system's resonant frequencies or resonance frequencies. Now, at resonant frequencies, a small periodic driving force they has the ability to produce large amplitude oscillation. So that you have to get it that at these various resonant frequencies, there is this small periodic driving force that is there can have the ability to produce large amplitude oscillations. Now, this is because the system stores the vibrational energy. Now, resonance it occurs when the system is just able to store and easily transfer energy between two or more different storage modes, such as the kinetic energy and the potential energy in the case of, for example, of a pendulum. Now, however, there are some losses from the cycle to cycle called the damping. When damping is small, the resonant frequency is approximately equal to the natural frequency of the system, which is the frequency of unforced vibrations. Some systems they have multiple distinct resonant frequencies. Uh, that's how you can tell there are various systems out there that can be involved with these kinds of various resonance. Now, let's see these kinds of resonance. We'll start here with the resonance in closed end pipes. Now, a closed-ended instrument has one end closed off and the other end open. Now, an example would be an instrument like some organ pipes, although in some designs they are open, or a flute. So, that is an example of a closed-ended pipe instrument. Now, although you blow in through the mouthpiece of a flute, the opening you're blowing into isn't at the end of the pipe. It's just along the side of the flute. Now, the end of the pipe is closed off near the mouthpiece. Now, just remember that it's actual air that is doing the vibrating as the wave here within the instrument. Now, the air at the closed end of the pipe must be a node, yes, not moving. Since the air is not free to move there, it must be able to be reflected back. Now, from there must be also be an antinode where the opening is, since that is where there is maximum movement of the air. The simplest, smallest wave that can possibly fit in a closed-end pipe is shown in figure below. We'll see the figure now that we just portray as the fundamental. Notice how even though it has been flipped left to right from the figure and it looks squashed and stretched a bit to fit, there's still just a quarter of the wavelength. Now, since this is the small stable piece of the wave I can fit in this pipe, now this is the fundamental or the first harmonic. And here is the diagram of it, the diagram of the fundamental or the first harmonic. In response to the just the resonance that can occur in the closed end pipe. Now, considering the diagram, since the length of the tube is the same as the length of the quarter of the wavelength, now I know that the length of the tube is just a quarter of the wavelength. Now, this leads to our first formula, that is L is equal to a quarter lambda. Now, L is just the length of the tube in meters. Now, on its own, this formula just doesn't really help us much, because we need just to see what happens when we need to get to the second harmonic, the third harmonic, the fifth harmonic for the closed end pipes. Now, instead, we have to solve this formula for lambda and then combine it with the formula B is equal to F lambda just to get more useful formula. Now, from there, L is equal to a quarter lambda. Lambda is equal to 4L. Now, V is equal to F lambda. We know that. So, V is equal to F, then times 4L. Now, if you make F the subject, you will be equal to V upon V upon 4L. Now, F is just the frequency of the sound, V is just the velocity of the sound in air in meter per second, then length is the length of the tube. Now, considering this table, that will result to our next explanation here we have. Now, when the wave reaches the closed end, it's going to be reflected as an inverted wave going from air to whatever the pipe is made of. This is a pretty big change. So this is what we would expect. Now, it would look like the from the figure above. Now, this just does not change the length of the wave in our formula, since we are only seeing the reflection of the wave that has already existed in the pipe. Now, what does the next harmonic look like? Now, that is what we would see. That is the third harmonic. Now, in fact, all the harmonics in the closed end pipes are just odd numbers, so you cannot find the second harmonic or the fourth harmonic in the closed end pipes. You just find these harmonics as in odd numbers. And here, considering this diagram, will just let us know about the third harmonic within the closed end pipes. Now, remember that we have to have an antinode at the opening where the air is moving, and a node at the closed end where the air cannot move. That means that the third harmonic we get something like figure above, as we've seen the figure. Now, this is just the third quarter of the wavelength fit in the tube. So the length of the tube is L is equal to 3 upon 4 lambda. Now, this is just the third harmonic of the closed end pipe. The formula for the frequency of the note here is just like this. F is equal to 3V upon 4L. So that's the formula. Now, if we drew in the reflection of the third harmonic, it will look like the figure below. So this is the figure displaying the third harmonic with considering the reflection within this closed end pipe. Now, from the figure, we'll just get to the fifth harmonic. There's one full wavelength in there that is for 4 plus an extra 1/4 of a wavelength of a total of 5 a quarter. Now, the length of the pipe is just L is equal to 5/4 lambda, and the knot produced by the fifth harmonic is found using the formula F is equal to 5V upon 4L. Now, figure below, then it will show the reflection of the fifth harmonic for the closed end pipe. So this is the figure showing the fifth harmonic, showing the reflection of this fifth harmonic for the closed end pipe. Of the clear? Now let's move on to the other part, discussing about the resonance, talking about the open end pipes. Now, an open-ended instrument has both ends open to the air. An example would be an instrument like a trumpet. Now, you go in through one end and the sound comes out the other end of the pipe. And for the fundamental of the open end pipe, we will find it looks like this. So this is the fundamental for the open end pipes. Now, considering that diagram, the fundamental, that is the first harmonic, for an open end pipe needs just to be an antinode at both ends, since the air can move at both ends. Now, that's why the smallest wave we can fit is just shown in the figure, as we've seen in the figure above. Now, this just looks different than the half wavelength that I've shown you in the figure for the closed one when we were discussing the fundamental for the closed end pipe, but it's still half of the full length. Half of the full wavelength. Now, this that means that the length of the tube and the frequency formulas are just L is equal to half lambda, whereby F will be equal to V upon 2L. Now, the next note we can play is the second harmonic. Yep, open end pipes, they have second harmonic. They can have any number harmonic they want, odd or even. So, comparing to the closed, whereby they can have only have this odd number harmonics. So in open end pipes, they can have both. They can have any kind or any number of the harmonic they want, odd or even. Now the length of the frequency formula, just L is equal to 2 upon 2 lambda, where F will be equal to 2V upon 2L. Now from there you can go on to get the third harmonic, the fourth harmonic, etc. Now the formula for the length and the frequency that L is equal to 3 over 2 lambda, whereby F is equal to 3V upon 2L. Now you can use this formula to obtain the third harmonic, the fourth harmonic for the open end pipes. And here is just the diagram of the second harmonic, how it looks like. So you can compare these harmonics, the second harmonic, considering with the third harmonic to the closed end pipes. So that's all I have for this session of the script, and thank you for listening. We've discussed about the resonance. We've seen the meaning of the resonance, and we've seen how the resonance can occur in closed and the open end pipes. So that's all I have for this session, and thank you.